So 250 times 0.75 to the third. So there I get $105.47. And then for part C, to find the bike's value when the bike's value is $100. So I can see right away it's going to be pretty close to 3 years, just a little bit after. But let's go ahead and do it in our calculator anyway. So I'll type in my model and put 100 in for my other equation. Set my window, so I know it's going to happen right around 3 years, so I don't need my x to be very big. I know the maximum value for the bike was 250, so that looks good there. So we'll draw our graph. There's my intersection. So to find that intersection, now I press second trace, choose the intersect command, select one of the two curves that I'm looking for the intersection on, select the other one, and then just move my cursor over somewhere close to the intersection for my guess. So I would say 3.19 years after purchase. Are you okay with that, Dan? Okay. Anyone else with questions from this assignment? All the problems were pretty much the same, right? You had to use different model for different problem, perhaps, but not too much different in terms of your steps there. Jack? For 5? Was the issue knowing what to do with 7 years and 3 months?
No, I just
Okay. So for part A, we did this. Oops, T. Okay. For part B, I need to figure out a value for T, where T is time in years. So I need to convert 3 months into some fraction of a year. So how many months are there in a year? 12. So 3 months is how much of a year? Yeah, like 0.25, right? A quarter of a year. So I'll just put in 7.25. Everybody's okay with that idea? So that's how all I do for B. I just type that into my calculator then. Annalise?
So we need to figure out like that 3 is a quarter. 3 months is a quarter.
T is time in years in our formula. So I had to rewrite 7 years and 3 months as just years. Right? So that's 3 months is a quarter of a year. Right? Because there's 12 months in a year.
So like, is it a certain amount of like minutes or like seconds and minutes? You have to like make it all seconds.
You'd have to turn it, well, for this model, T is in years. So the unit for T has to be years.
Oh.
Okay? So it a little bit depends on what's going on with your rate of change, but interest rates are annual. When you're quoted an interest rate, they're always quoted annually. So the T is in years. So the T has to match your rate of change. And for a banking problem, the interest rates are always like industry standard is yearly. So the T is in years, if that makes any sense.
Mm-hmm.
Jack, are you okay still?
Yeah, I know that's wrong.
Okay. And then for part C, this is a calculator problem. So my first equation, 10,500 times 1 plus 103 divided by 365 to the 365x, and then 1 million for the other. For my window, probably going to take a while to get that thing worth $1 million. I don't know, I'm going to just guess 50. And then my minimum was the starting amount. And my maximum needs to be bigger than $1 million. So I'm going to pick 1.5 million. That's right. Number of spaces. So here's my curve. And there's the $1 million line. So there's my intersection right there. So again, we go second trace, select the intersect command, pick each of the two curves we're interested in, and then scroll over for our guess. And just as a reminder, when we're picking these windows, a good window is just one where you can see the intersection, right? You don't have to use the same numbers that I used. Doesn't have to look exactly like mine looks. As long as you can see where they intersect, that's a good window. So there, for this part, 44.25. Years after our initial deposit. That's not too bad, though, to make $1 million just sitting on your duff. You had to wait a long time, but, you know, it's pretty nice to, like, walk away 40 years later and be like, oh, look at that, I had $1 million I kind of forgot about. Elena. So I usually just try to use the information that's given to me in the problem. So to some extent, I'm just kind of guessing, but I'm trying to make like an intelligent guess based on the problem. So here, when I did this part, my answer was like, I don't remember, it was like 20,000 or something. So it didn't change a lot after 7 years. That's why I knew that it was going to take a while to get there. So I picked the X to be kind of big out to 50. Dude picked 100 or 200 or whatever. Like, you know, that seems not not a bad guess there. But it was just kind of a guess. And then the Y's, again, I took the smallest Y, the smallest amount the account is worth is what it had initially. And it needs to be bigger than $1 million, so I picked some number bigger than $1 million. So again, like, all you really need to be able to do is see the intersection, though. So like, even if you're kind of a bad guesser at things, as long as you can see the two things crossing, that's all you need. Anybody else questions on these? Okay. Good. All right. So the next section we're going to talk, or next topic we're going to talk about is this special number that we're going to give the name to E. So we're going to refer to this special number as E. So let's think back to our compound interest formula here. And we're going to make a couple of assumptions to simplify things a little bit. So we're just going to take everything other than n and just set it equal to 1. Because what we're really interested in here is kind of this value for n. Remember what n represented in this formula? It was the number of compounds per year, right? So it's like, how many times does that, that account kind of change in value, right? That's what that means. How many times is that interest paid in there? We can extend this idea to talk about like other systems other than just like a banking system. So let's think about this in terms of like a population. Let's say the population of human beings on the planet. How many people are there on Earth right now? About 7 billion, okay? And how often do you think that population is changing? Like all the time, right? There's a lot of individuals. There's going to be people that are dying and going to be babies being born kind of all the time, right? What kind of value of n would we use there? So something is happening. We're having change all the time, right? How many times would you say then the population changes in a year? Why is it a hard question? Maybe it's not looking for an exact answer. Andrew? Infinite. Yeah, that's kind of where we're heading towards, right? Like it's going to be more or less uncountable how many times that happens, right? So really what we're going to be interested in is going to be applying this model to like a biological system where change is happening like all the time, where n is approaching infinity. So think about another situation. Say you have like an organism that's growing, like you have a baby, and you're describing like the height or the length of the baby. How often is a baby growing? All the time, right? It's just imperceptibly small. 6 months later, you realize, oh, that baby grew like 4 inches But at the moment, like you can't watch it and grow. It's happening very slowly all the time, right? Like infinite time, there's infinite number of times where that baby is like growing a little bit. It's just really small. So that's really kind of representing when n goes to infinity. Now, can we go ahead and plug infinity in to this function and evaluate and get a number? No. What we can do, though, is we can kind of get an idea of what that number is going to look like. So I'm just going to pick some values of n and see what I get for my value for fv. So I'm just going to pick some progressively larger and larger values for n. And just kind of see what we get for fv. Oops. Okay. So when I plug 1 in for n, I just get 2. When I plug 10 in for n, I get 2.59 and some decimals here. Then let's plug 100 in. So there I get 2.7. And then let's plug 1,000 in. And there I get 2.716923932. Let's take a pause here and kind of look at what's going on. So how is FV changing when n is getting progressively bigger here? What did you say? So it is increasing. Is it increasing the same amount each time? No. Is it increasing more or less each time? Less, right? In fact, it looks like it's probably going to be settling down to a specific value. So notice here, the first digit matches. And then eventually we get 2 digits that match. Let's see what happens when we put 10,000 in. So now how many digits do we have matching? Now we have 3 that match, right? Let's do the 100,000. Think we're going to pick up another digit? Maybe. Sometimes we will, sometimes we won't, you know. It's hard to say. Oops. What did I do here? Do I have too many digits here? Yes, I do. I think I have 1,000,000 there instead of 100,000. There we go. It's like, that's not right. I just must have fat-fingered my calculator, you know? That's what I call it when you press the wrong button. Like you had fat fingers and they got in the way. Okay? And so now when we look here, we have 4 digits that match, right? And we could keep doing this, picking bigger and bigger values of n, and get more and more digits of whatever this number is. What I'm going to do here real quick is just pick the biggest number that can fit into my calculator, which is 1 times 10 to the 99th. I think I better do that. Oh, you gotta be joking me, calculator. All right, well, it's not gonna do that. So we're gonna say that this value is equal to this number e as n goes to infinity. And the value for e is approximately 2.7182818, yada, yada, yada. But this is one of those irrational numbers. That is that it's a number that goes on forever, that it doesn't change or doesn't repeat itself. There's no pattern. It's like the number for pi, right? And just like for the number pi, we give it a special name because we don't want to write down like all the decimal places for it. Everybody okay with that idea? We chose to give this number the name E because of the mathematician that first kind of did this work. His name was Leonard Euler. And we used the letter E in honor of his last name there. I don't know if there's anything. That's just a fun fact. So what this does is it gives us a new model that we can use when things are happening all the time. So that continuous change model is FV is equal to PV times e to the RT Okay, so FV is the future value, PV is the present value. E is just that irrational number that we described before. R is our rate of change written as a decimal. And then T is time. And the unit for time there should match the rate, the unit on the rate. Typically it's going to be years, but it need not have to be. Okay. So there's two kinds of application kind of problems that we might ask you to do with this information. One of them is work with a model that I've already given you that includes a E in it. So let's take, for example, this. Oops. Okay, so the length L of a tiger shark can be modeled by the equation. L is equal to 337 minus 276 times e to the negative 0.78 t, where t is the shark's age in years. So if we ask you to estimate the length of a 3-year-old shark, what do we want to do there? Yeah, we're just going to plug 3 in for t. Oops. Put the 3 in. And just like pi, our calculator has e built into it. So 337 minus 267. And there's 2 places where I can get the letter e from. The one that I usually use is by pressing second and the ln button. You'll notice that's on the left-hand side of your calculator. I like that option because it gives me an exponent with it at the same time, and almost always I'm putting an e to some power when I'm doing this work in this chapter. So it just saves me an extra button having to press the exponent button. Those of you with calculators and that are following along, were you able to find the second and then ln buttons to get your e to pop up? It's pretty easy, right? Okay. So there we have about 180 centimeters. Next up, we're going to ask you to estimate the age of a 3-meter shark. What am I looking for here? The value for t. Okay, so I'm going to have to plug in a value for L to get that. What value of L am I going to plug in? What? 300. Why 300? Yeah, we need to make sure that we've written our L in centimeters. So 3 meters is 300 centimeters. So this is the equation that we're going to solve. And we can just use our calculator to do this. So 337 minus 267 times second ln negative 0.178x and then 300. Okay, so let's make a window. Anybody know anything about sharks in an abstract kind of sense? Like, how old do you think a shark can get? Pretty old, right? I don't know, 30, 40, 50 years, something like that is probably not unreasonable. It's a pretty big animal. There's no obvious predator to it. Big animals usually can live for a long time. So let's pick 50 maybe. My minimum length for a shark, well, that's probably 0, since A zero-length shark is one that just hasn't been born yet, right? And the length that I have to get higher than is 300, so I don't know, maybe 350 as my Y max. Just going to pick something bigger than 300. So there's my curve for my shark length. There's my 300 line, so I can see my intersection right there. So second, trace, intersect, curve 1, curve 2, and then I guess so 11.1 years old. Everybody okay with that? So very much just like the things that we got done doing, right? The only difference is that the equation can have an e in it, but we understand what e is now. It's just a number, so it's not like pi. It's not a big deal. The other kind of problem we'll ask you to do from this section is one where we have to write our own equation. So you deposit $2,500 in an account that earns 5% interest compounded continuously. Find the balance after 10 years. What word inside of this story problem should be like looking at you in like flashing red letters that's the most important word in this problem? Yeah. Continuously. What is that telling me? It tells me that I need to use the model with the e in it, not our usual compound interest model. Everybody's okay with that idea? So that's very important. You look for that word continuously. That's your clue that you need to be using this model with the e in it rather than the compound interest model. All right, so we're looking for a future value. So the present value is 2,500. The interest was 0.05 and our t was 10. So we can just plug all this stuff in. 2,500 times second ln 0.05 times 10. That gives me $4,121.80. I think I copied that right. Oh, good. Do you feel okay doing this? Okay. So if you guys, that'll finish up that section for us. If you guys remember, when we started this chapter, we said it was going to be about exponential functions and logarithmic functions. Yeah. So we've been talking about exponentials for a good bit here. It's time to talk about logarithmics here before we start mixing the two together, because they are very closely related. So the next section, we're going to start talking about the logarithm and defining what we mean by a logarithm. But before I do that, I'm going to ask some hard questions. These are going to be hard questions because you're going to have to remember. from a way back at the beginning of first semester. Okay. Who remembers what a function is? Anybody? What is a function? That's function notation, sure, but what's the definition? It's a set of ordered pairs. So x's and y's that have what property?
Only one x equals one y, right?
Okay. Every x pairs with exactly one y. Good. Okay. So, for example, is this a function?
Yes.
Yes, right? My x's are 1, 2, and 3. 1 is paired with just one number. 2 is paired with just one number. 3 is paired with just one number. Okay? We also talked about around the same time as this about inverse functions. Does anybody remember how to find what the inverse function is, or how to find the inverse of, say, this set 1, 2, 2, 3, 3, 4? Okay, so let's think about it a little bit. When we just say the word inverse in an English language sense, what does that mean? Okay, like an opposite. So what would the opposite be of that set of ordered pairs there? What was that? There you go. So if this is f inverse would be 2, 1, 3, 2, 4, 3, right? Where we're swapping the x and y coordinates. In a English language sense, we're inverting them, right? Switching their locations. The mathematical word for that is transpose, when you switch the locations of two objects. I'm guessing most of us aren't familiar with that word, though. Okay. Now this is nice. It's easy to find the inverse if our function is written as a set of ordered pairs, right? What if our function is written as an equation? Because that's really, after we escape this first chapter, that's how we've written all of our functions from there on out, right? Written them as an equation rather than a set of ordered pairs. So how do I find the inverse for an equation? Or how do I test that two things are inverses? What's that definition look like? So we say that two functions f and g are inverses if and only if f compose g of x is equal to g compose f of x, which is equal to x. We did learn this. This is all review from first semester. So let's say that we have these two functions, f of x and g of x, and I want to show that they're inverses. Yeah, so you're right. What this means is that, and this one would mean that. Yup. So what are we going to do then? If I want to do f of g of x, I'm going to take my equation for g and plug it into the x in f. Everybody's okay there? So notice that in that parentheses, I have a times 2 and a divided by 2, right? What's going to happen there? Cancel out. So I'm left with x minus 5 and a plus 5. What's going to happen there? Yeah, the minus 5 and the plus 5 are going to cancel out. And I'm left with just x, which is what we wanted to show, right? Everybody okay there? Good. All right. So that's how we can determine two things are inverses. How do I find the inverse? Because there must be a way to do it, because Mr. Kulik just made up this example real quick and was able to write down two things that were inverses. So it must be a way to find the inverse for a function that's not that hard, since he did it in his head. Does anybody remember how to do this? Okay. So the first thing I'm going to do is I'm going to just rewrite f of x as y. Remember, this still kind of means the same thing. And then I'm going to basically get the x by itself. So I would subtract 5 from both sides. I can't subtract 5 from a variable, so I'll just write y minus 5. And then I'll divide both sides by 2, and I can't divide y by, or a variable by a number, so I'll just write it as y minus 5 over 2. So now the x has been isolated. Everybody's good with this? It's pretty easy to do that. My last step then is going to be to swap the x and y. So everywhere there was a y, I'm going to write an x, and everywhere there was an x, I'm going to write a y. And I'm going to call this new equation a new function name, let's say g. So there, g of x is equal to x minus 5. So f and g are inverses. Everybody's okay with that idea? Okay. So why did we go through all of this? Because exponential functions and logarithmic functions are inverses of each other, and the definition for a logarithm reflects that. So we say let b and y be positive numbers where b is not equal to 1. The logarithm of y with base b is denoted log subscript b parenthesis y parenthesis. And it's defined as log base b of y is equal to x if and only if b to the x is equal to y. So what is a logarithm describing? It's describing the exponent for a certain problem that has a certain base and is equal to a certain value. This is exactly the kind of problem that we were forced to use our calculator to graph and solve for in the previous homework assignments. We're now going to develop a method for us to be able to do this algebraically, as we're going to define this new operation called a logarithm that's going to allow us to do this without having to graph and find the intersection. Before we do that, though, okay, so let's say that we have log base 2 of 8 is equal to 3. And I want to rewrite that in the exponential form. So the base of my logarithm is 2. So that's going to be the base of my exponential. The argument for my logarithm here, the y, is 8. That's going to be the solution to this exponential equation. The answer to this logarithmic equation is going to be the exponent in my exponential equation. So let me ask you, is 2 to the third equal to 8? Does that make sense? Yeah, that's true, right? So that also means log base b, or log base 2 of 8 is 3. What this is saying is, what is the exponent in this equation? 2 to what power gives me 8? And the answer to that is 3. So what the logarithm is doing is it's telling you what exponent you need to solve this exponential equation. Is everybody kind of okay with that idea?
Can you say that last again?
So it's giving you the exponent that solves this exponential equation. Let's do another. Actually, let's do something. Do that. Okay. So here we have log base 3 of 9 is equal to 2. Okay. So which one of these three numbers is the base of my exponential? 3, 9, or 2? 3. Great. What's the solution to this exponential equation? 9 or 2? 9. And what's the exponent in this exponential equation? 2. And does this make sense? Is 3 squared equal to 9? Yes. What do you guys think? So far, so good? What if we ask you to go the other direction? So if we have 4 to the third is equal to 64. So I'm going to have log. What's the base for my exponential? 4. What's the base for my logarithm then? 4. Okay. What's the solution to my exponential equation? 64. So that's the argument for my logarithm. And the exponent in my exponential equation is the solution to my logarithmic equation. So again, I'm just using that definition up here and saying, okay, b, x, and y, and plugging them into the right places in the logarithmic equation. Is everybody okay with that? What do you guys think? Not too bad? Okay, we'll stop here. We'll dive in deeper with